This video introduces sets and some basic notation and definitions. Informally, a set is a collection of objects or members. Here are some examples of sets. Let's let C be the set containing all the colors of the rainbow. When we write a set using these curly braces and we list all its members with commas between them, that's called list notation. Let's let B be the set of x such that x is an integer that has a remainder of 1 when divided by 3. When we describe a set by giving a property that all its members share, that's called set builder notation. In set builder notation, we start with a variable, then a vertical line that reads such that, and then a description of the property that that variable needs to satisfy. Another example of a set is the empty set, also called the null set. The empty set doesn't have anything inside it. That's why it's called empty. Sometimes the empty set is also written just with curly braces with nothing inside. We say that little a is an element of a set big A, written in this notation, if little a is an object or a member in big A. Let's consider the same two sets before, the set of colors of the rainbow and the set of integers that have a remainder of 1 when divided by 3. Please take a moment to decide if these statements are true or false. It's not true that pink is an element of C, since C only contains the colors red, orange, yellow, green, blue, indigo, and violet. In fact, we can write that pink is not an element of C. Now it is true that 4 is an element of B, since 4 is an integer, and 4 does have a remainder of 1 when divided by 3. The last statement is false. The empty set is not an element of the empty set because the empty set has no elements. I want to make a note here that the order of the elements when we use list notation doesn't matter. For example, we could write C like this, or even like this, where some of the elements are repeated, and it's still the same set. Two sets A and B are called equal, written A equal to B, if they contain all the same elements. More formally, we could write this as for all x, x is an element of A, if and only if x is an element of B. A set A is a subset of B, written in this notation, if all the elements of A are also elements of B. More formally, I could write this as for all x, x is an element of A implies x is an element of B. A set A is a proper subset of a set B, written with this notation, if A is a subset of B and A is not equal to B. For example, if A is the set containing the numbers 1, 2, 3, and B is the set containing the numbers 1, 2, 3, and 7, then A is a proper subset of B. As a Venn diagram, you can think of A as being contained in B, but not taking up the whole thing. Note that if A is a proper subset of B, then A is a subset of B. Also, if A is equal to B, then A is a subset of B. This is analogous to the fact with numbers that if x is less than y, then x is less than or equal to y, and if x is equal to y, then x is also less than or equal to y. For each pair of sets below, we'll call the first set A and the second set B. See if you can figure out whether A is equal to B, A is a proper subset of B, B is a proper subset of A, or possibly none of these relationships hold. Note that this letter Z represents the set of integers. The first example, for these intervals using interval notation, A is a proper subset of B. Every number that's in this interval is also in this interval, but there's some things in this interval that are not in this interval, so the two sets aren't equal. For the second example, I'm going to rewrite A and B to make them easier for me to think about. I'll write A as 1, 3, 5, 7, 9, and B is the set of x's such that x is an odd integer greater than 0 and less than 10. So that's going to be the integers 1, 3, 5, 7, 9 also. So A is equal to B. They're just described in two different notations. In the third example, A is a subset of B. In other words, the empty set is a subset of the set of integers. That's because if an element X is in the empty set, then X has got to be in the set of integers is vacuously true. Because there are no X's in the empty set. So in this if-then statement, the premise is false, and so the if-then is true. Another way of thinking about this is that all elements of the empty set are in Z because there are no elements of the empty set. In fact, the empty set is a subset of any set S, and the empty set is a proper subset of any set S if S is not itself the empty set. The cardinality of a set A, written with these absolute value signs, is the number of elements in A if A contains finitely many elements. And for now, we'll say that the cardinality is infinity otherwise. Later on, we'll refine this definition when we talk about different sizes of infinity. So for example, if C is the interval of real numbers between 0 and 1, including 1 but not 0, then its cardinality is going to be infinite. If D is the set of odd integers greater than 0 and less than 10, remember we said that this is just the set containing 1, 3, 5, 7, and 9, then this cardinality of D is going to be 5. Given a set S, the power set of S, written with this curly P, is the set of all subsets of S. This can be written in set notation, set builder notation, as the set of x's such that x is a subset of S. If we want to find the power set of the set A, consisting of the integers 3, 6, and 9, let's start by writing down all the subsets. There are 3 subsets with cardinality 1, in other words, containing just one element, 3 with 2 elements in them, one subset that contains all 3 elements, and don't forget about the empty set with no elements. So the power set of A is the set containing all these subsets. There are 8 subsets altogether, so the cardinality of the power set of A is 8. In this video, we defined various notions related to sets, including subsets, proper subsets, cardinality, and the power set.